Alright, so near the beginning of this chapter I said that color and temperature are going to be interchangeable. And this is what I mean. Star color is star temperature. So if it's red, like Betelgeuse up there, it's going to be cooler. If it's blue, like Regal down at the bottom, it's going to be hotter. So the bluer the color, the hotter it is. Okay. Now, you're thinking, yeah, but when I use the restroom and the sink or whatnot, blue means cold, red means... Yeah, but we're not talking about that type of temperature-color relation. We're talking about blowtorch. Right? If you ever seen a blowtorch or used a Bunsen burner, you wanted the blue flame because that meant it was hotter. Right? So that's the kind of color scale we're using here. Red is cooler, blue is hotter. All right, so how do we do this color analogy? Well, you have to measure the star or the light source at different wavelengths. And then you draw a black body. Remember, black body does not mean it's black. Black body is the mathematical line that tells you where it will peak in each different zone. So the third one down there is the sun. You can see the sun actually peaks in the visible spectrum. And the sun is about 6,000 degrees Kelvin. Now, you'll also see, if you look at the top one, that black body line does not even reach the visible, which means that it doesn't peak in the visible, which means you can't even see it in the visible, right? And then the next one down, you can start to see it in the visible, but that's not where it's peaking. That's not where it's going to be brightest. And same with this bottom one, right? You can see it in the visible, but it's not peaking there. That's not where it's going to be brightest. So the temperatures of the stars are kind of given on the color, which translates to what type of light is it radiating. Now, what's really interesting about this is that you can determine its black body line or a black body spectrum from only two wavelengths. We call it the blue filter, or the B filter, and the V filter. So the blue-violet filter and the green-yellow filter. And by looking at those two wavelengths, you'll be able to figure out its black body spectrum, because no black body spectrum is the same. They're all unique. Alright, so here's kind of an example. 3 different black body spectrums using those two filters. Right? And so you can see line A. It's actually peaking closer to the ultraviolet. It's 30,000 degrees Kelvin. It's more blue. Right? C, on the other hand, is more yellow. You can see it's kind of going downhill already by the time it hits the yellow and the blue. And so C will appear to us as more yellow. So it's going to be cooler. It's actually 3,000 degrees Kelvin. So again, you just need these two filters, the B and the V, and you can make a black body curve, which will give you the temperature of the star. So once again, color is temperature, right? Red is the coolest, blue is the hottest. And stars we found go from about 3,000 degrees Kelvin to 30,000 degrees Kelvin. And you can see the colors there, red all the way to electric blue. And you can see our sun is in the yellow. So we've talked about this before, absorption and emission lines, right? And how you can tell what elements are in which star based on these lines. Chapter 3. However, you can also use these to tell its temperature. So not only does the absorption and emission lines tell us composition, it also tells us temperature. So what's kind of interesting in how that works is that for stars greater than 25,000 degrees Kelvin, they're going to have long, strong absorption lines for helium. And you can kind of see that there, right? Look at the 30,000 and then like the 6,000, right? Helium is a lot bigger of an area, and there's not much going on there. Now stars at about 10,000 degrees Kelvin are going to have strong hydrogen lines. Anything weaker than 4,000, so we're looking at the 3,000, you're going to have weak absorption lines. And this is due because you're going to have a lot more molecules, a lot more stuff in it, right? So if it has a lot more stuff, its temperature is going to be a lot lower. And you can see that, right, look at the bottom one. It's just got absorption lines galore versus the top one that only has a few. So it turns out, even though these absorption lines differ, all stars are basically hydrogen and helium almost 100% of the time, with maybe 1% or so of other, right? So the reason why the absorption lines look different is because of temperature. So the temperature is why you get all these different absorption lines. Stars were classified by letters, A through P. But then as science got better, new classifications came out based on the temperatures, and rather than renaming everything, they just reordered it. So it's OBAFGKM, where O is the hottest and M is the coolest. And again, the little acronym they use to remember it is O be a fine guy, girl, kiss me. Now each of these are subdivided into 10 divisions from 0 through 9. Okay, so the lower the number, the hotter the star. So an F9 star is warmer than a G2 star. Well, fine guy girl, right? So F comes before G, so it's hotter. Even though the 9 is higher than the 2, it's still got that first category. Now, we are a G2 star. By we, I mean the sun is a G2 star.